Hello, I'm Jan Gray. Today I'm presenting an overview of the design and rationale for our proposed specification for RISC-V Composable Custom Extensions. For the past several years, this group of RISC-V FPGA soft processor designers and users have met online to design standards for adding custom instructions to the RISC-V soft processor cores, culminating in the present spec. The outline of the talk follows the outline of the spec, and there will be section numbers so you can follow along in the spec if you wish. To appreciate the RISC-V custom extensions reuse problem, let's talk about RISC-V extensions. There's the RISC-V base ISA and standard extensions like floating point and atomics that layer and compose correctly on top of that. There's also a community process to define a new standard extension, which must be of general interest and broad utility and non-proprietary. It can take a long time to define a new extension, and in the end, each new standard extension consumes some of the remaining 32-bit instruction opcode space and adds to the enduring complexity of RISC-V. Now, from the very beginning, RISC-V has also supported custom extensions. The custom 0, 1, 2, 3 opcode blocks will never be used by standard extensions, and that enables rapid development of domain-specific, problem-optimized custom extensions and their software libraries. This is very good, and it helps make RISC-V an agile platform. However, your custom extension in software may not work correctly alongside my custom extension in software when run together within one system. We may have used the same custom opcodes for different purposes, and beyond that, we may have different means of extension discovery, models of computation and state, error handling, different tooling, different versioning systems, different hardware logic interfaces, such as these here. Unfortunately, this leads to disjoint solution silos where we can't build on each other's good work, and to fragmentation of the RISC-V ecosystem. Instead, our specification enables and anticipates an ecosystem of mix-and-match composable custom extensions, where each combines the agility of custom extensions with the guaranteed correct composability of the standard extensions. This will require that we adopt common software and hardware interoperation interfaces so that our custom extension solutions can coexist together within one system. If we do this, then anyone, individual, company, school, or group, can rapidly define, develop, and reuse a new custom extension, its software libraries, its hardware implementations, CPUs that these all snap together into, systems composed of these, and open tooling for the same. We also believe that guaranteed composable custom extensions can help keep RISC-V simple by reducing the pressure to add essential but domain-specific standard extensions. Indeed, we agree with this fellow, whose soapbox is that a RISC-V extension that can be a composable custom extension should only be a composable custom extension. There are three key elements or concepts necessary to understanding the specification. The first is a composable extension, CX. That's the interface contract of a composable custom extension. It consists of the custom function instructions and the semantics of the custom extension. For example, the order the instructions must be used. It's immutable, meaning once defined it must never change, and it's named with a unique 128-bit GUID, that's a globally unique ID. Next is the composable extension unit, CXU. That's a modular, reusable hardware core that implements one or more composable extensions. And finally, there's the composable extension library, or CXLib. That is software that first selects the current composable extension prior to issuing its custom instructions. This shows how it all works together. Alice is building a system on a chip. She starts with a system manifest declaring that her system shall have two CXU-compliant CPUs and a cryptography CXU, which is needed by her cryptography library. She obtains reusable packages for these cores, and she runs a composer tool which configures the cores and assembles them into a processor complex according to the manifest. The composer also emits a system CXU map with one entry indicating that the cryptography composable extension is available and is implemented by CXU number 0. Alice's software application includes a crypt library and a compression library. The crypt library uses the CX runtime to discover that the cryptography extension is available, and so it uses the custom cryptography instructions that issue into the crypt CXU. Next, Alice updates the system manifest, adding the compression extension package, and rebuilds the system and CXU map, adding a second entry for the compression extension and its CXU number 1. Now, when Alice runs the application, both her crypt library and the compression library discover that their respective extensions are present in this system, and each issues their custom instructions upon their respective extensions' CXUs. Later, Bob takes Alice's SoC design and retargets it to a different FPGA from vendor B. He upgrades the processors to B CPU cores, and he rebuilds the system, which just works. Bob shudders a bit, remembering how difficult this used to be. Then, after profiling the system, Bob realizes he needs to accelerate his ML inference library. He designs a binary neural network composable custom extension that's a CXU that implements its custom instructions, and a CX library that discovers, selects, and issues its custom instructions. He builds this system again, and now all three custom extensions and their libraries work together, each accelerating different parts of the workload. To appreciate the various moving parts of the specification, it's helpful to understand our design objectives. Of paramount concern was composition. We could not use any idea that would break correct composition. It has to be easy, robust, routine, even boring, to add a composable extension to your system, without ever worrying that the rest of the system may come crashing down. And as extensions, CPUs, CXUs, and libraries will be authored across organizations, across decades, across platforms and tools. That also constrains our solution space. We also wanted a decentralized solution with no central assigned naming or numbering authority, no gatekeeping, and no asking for permission. We wanted to accommodate a diversity of RISC-V systems and workloads, from tiny MCUs to many core Linux servers. We wanted interfaces that are open and non-proprietary and free, so that extensions can be reused across platforms and tool stacks. We paid a lot of attention to efficiency, favoring the simplest possible mechanisms, the most hardware-frugal mechanisms, and the fastest code paths. We decided that composition must not require recompilation of libraries or regeneration of RTL cores. This is a fundamental decision in the design. When multiple extensions are composed together, you're going to have to do something so that, for example, their opcodes do not conflict. And one approach is to compute configuration-specific assignments of custom function IDs per system, and then recompile libraries or statically relink applications to fix up previously conflicting indices. But we rejected this. We felt it's too disruptive to software stacks and development processes. And anyway, people want to use one golden version of a binary across many systems configurations and across the years. Similarly, except for changing configuration parameters, we don't want to have to regenerate hardware composable extension unit cores each time they're composed into a new system. Now, with the big focus on security, we felt we needed to at least provide operating system access control to grant or deny access to composable extensions and their state. And finally, we wished to promote uniformity across extensions. And by uniformity, we mean that there should be one way of doing most things, a uniform way of naming, discovering, and versioning extensions, a uniform, unlimited, conflict-free way of encoding the custom instructions, a uniform means for managing the state and context save restore of stateful extensions, uniform error mechanisms, and uniform access control. Uniform hardware logic interfaces and metadata to make it easier to compose and test extension implementations. And in general, one good enough way to do these things versus inventing many incompatible ways and the fragmentation that comes with that. Somewhat unusually, we propose two interop interface standard layers. Up in the ISA hardware-software interface is composable extension multiplexing, which we'd like to call -ZI-CX. That would be a standard ABI for composition of extensions and libraries that first selects the heart's current extension and state context prior to issuing its custom instructions. Then each extension can enjoy the full custom instruction encoding space without conflict. A second non-ISA layer at the hardware-hardware interface, the CXU logic interface, would be a signaling standard for reusing and composing CPUs and CXUs. Note that these can be provided separately or together. You can imagine a processor with -ZI-CX extension multiplexing, but using a proprietary means of adding composable extensions hardware. Or a processor that doesn't do extension multiplexing, but adopts CXU-LI, which enables reuse of the CXU ecosystem. But overall, these two interop standards will work much better together. So this illustrates where the new interfaces fit into the hardware-software stack. The first is the CX runtime, or CXRT here. This provides common CX library services, including extension discovery, selection, and state management. Then there's -ZI-CX, which you might think of as the composable extensions extension, which combines custom instructions with new CSRs that provide extension multiplexing. Then down in the hardware, the CXU logic interface and metadata provide glueless automatic composition of cores into systems. The scope of our work, that is, what kinds of custom extensions can we support, was the subject of much debate. As this is a composable extension specification, we support extensions that are invariant under composition. That is, extensions whose behaviors do not change when combined together alongside others. The common property of such extensions is that they are completely isolated from each other, or shared nothing. So for version 1 of the spec, the scope is narrowly defined as extensions whose custom function instructions access only the integer registers plus an isolated extension state. We do not support custom extension access to the floating point or vector registers, memory, CSRs, the program counter, instruction flow generally, or exceptions. It's very interesting to compare our design to some of the other less composable extension systems, but that's the subject of another presentation. The design supports both stateless and stateful custom instructions in these composable extensions. Custom function instructions can read or write the state context data of an extension, which can include private RAM, register files, or registers. But this state is private and isolated to that extension and inaccessible to anything else in the system. Within a system, each composable extension and its CXU are configured with some number of state contexts. There can be 0 or 1 per heart, or even a pool of 1,000 contexts. It's up to the system designer. And so you have multiple state contexts per extension per system. The spec also defines 4 standard custom function instructions, together called iState context, that provide uniform access to the state of any stateful composable extension. More on that in a later slide. Now, this narrow scoping seems pretty limiting. All you get is access to the integer registers in some state, but you can actually accomplish a remarkable amount with such composable extensions. For example, the entirety of the bitmanip specification are stateless custom functions of 2 integer registers or an immediate. So yes, bitmanip could have been a composable extension. Then looking at some stateful examples, Extension state registers provide simple, composable, uniform, extension-scoped CSRs. And state supports reductions, where the extension keeps a running sum or other work-in-progress state. So that's dot products and multi-precision math and so forth, without resort to 3 source register operand instructions. And since a CXU can access both its custom function ID and the raw instruction word, it can recode and arbitrarily reinterpret the fields of a custom instruction. So this supports a vector extension with private vector register file state contexts and custom instructions which can operate on any mix of vector registers and integer registers. State also enables cascading input operands across custom instructions. Here, a 2-instruction sequence feeds a custom function of 4 registers and an immediate. The state of an extension can be 1 or more channels, with message passing custom instructions composing the system with stream-based accelerators or other processing elements. In general, any instruction with private RAM can use custom instructions to write the RAM, to operate on data blocks within the RAM, and to read out the results data. So this will support block compression, encryption, matrix multiplies, and so forth. State also enables async extensions where some custom instructions launch long-running operations and complete, while others block or not, awaiting each result. So, with the very simple change to a processor, routing some ALU source operands out to a CXU request, and multiplexing CXU responses into a destination register writeback, you can enable diverse scenarios at very low cost and complexity. That said, in the long term, a composable extension facility should address more scenarios and access to other RISC-V processor resources. So here are some discussions we've had that are not in the spec, if you will, a preview of some things to come. First, it would be very powerful and complexity effective and area frugal to add the pulp stream semantic registers and 0 overhead loops to the CXU V1 extensions, allowing efficient streaming of memory-based operands through extensible CXU data paths. Or enable a composable extension that can directly access shared memory, an additional CXU to CFU request response channel back to the CPU would ensure correct interleaving of CPU instruction memory accesses with the memory accesses caused by the custom instructions. But to preserve composition, it will help to have a means to allocate disjoint, isolated shared memory regions across extensions. And perhaps we need a way to specify composable extension instructions beyond just the custom opcodes. We've also thought about adding register pairs as destination or perhaps source operands, at least in the CSU response writeback, to allow higher bandwidth access through a CXU. Finally, the CXU logic interface does not currently support speculative issue and subsequent cancellation of stateful custom instructions, so we may want to add that in. But with so much yet to do in adopting V1, we don't need to decide these questions now, but we'll keep them in mind to simplify later evolution. Now, finally, after all these preliminaries and rationale, we can discuss composable extension multiplexing in detail. It's quite simple. There's a new CSR called MCX Selector, which is programmed with the heart's current CXU ID and state ID prior to issuing custom instructions. MCX Selector determines which CXU processes this heart's custom function instructions. It's a bit analogous to the vector extension's setVL prefix instruction, which changes the behavior of the other vector instructions in its wake. As custom instructions issue, they are turned into CXU requests, which are sent out to the heart's selected CXU. That CXU performs each request, possibly updating some isolated local state, and then the CXU response data is written back to a destination register. The CX status register will accumulate any CXU response errors. CX status is analogous to the floating point FCSR register, which accumulates floating point errors. Now, when the custom extension multiplexing is enabled, it changes the behavior of the custom 0, 1, and 2 instructions. Custom 0 becomes CXReg, which sends a 10-bit function ID and 2 source operands to the CXU and writes a destination register. CXIM sends a function ID, a source register, and an immediate. And CXFlex sends 2 source operands and does not write a destination register. Flex is used to provide up to 2 source operands to an extension, as well as a 25-bit custom opcode field that the extension can interpret as it likes. Now this illustrates extension multiplexing hardware-software interface in more detail. Running the code on the left, we've just moved the value of x10 into the MCX selector CSR, and now we're executing the CXReg custom instruction that follows. This will create a CXU request comprising the CXU ID and state ID from MCX selector, the raw instruction and function index that's in the instruction, and 2 source data operands from the register file. This request selects a CXU, a state within that CXU, and provides operands to perform the selected custom function, possibly updating its state. Then response data is written back to the destination register, and any error response status accumulates in the CX status register. This extension multiplexing mechanism is necessary but insufficient to implement composable extensions and their libraries. So the CX runtime library is a set of common services provided to all the CX libraries. Services include extension discovery, which maps a composable extension GUID to a system configuration specific CXU ID index. State management, which manages state context IDs, as well as performs in a neutral way context save and restore of any custom extension state context. Managing CX selectors, and access control to the extensions in state. The runtime is implemented in software to keep extension hardware simple and frugal. The CX application binary interface pertains to management of MCX selector. To support nested function calls among composable extension libraries, the ABI requires callee save behavior. So if a function changes the heart's current MCX selector, that function must restore the original selector upon return. This must also occur on stack unwinds, including C++ exception handling. You can use a C++ RAII object to represent that scope nesting. So in the constructor, you would write the new selector value, and in the destructor, restore the original selector value. That will work in lieu of a CX ABI aware compiler, but in time we may use such a compiler to better insert and optimize these CX selector writes. Here's an example CX programming model. This is not particularly efficient, but it illustrates many of the features. Here again we use a C++ RAII, that's resource acquisition is initialization object, to scope the extension's custom instruction execution. This code discovers whether the ibitmanip extension identified by its GUID is configured in this system. And if so, it will write MCX selector, selecting the extension, and then issues a custom pop count instruction, and then in its destructor restores the original MCX selector value. If it's not configured in this system, the code falls back to a software pop count function. Now, if you do this in a loop, it redundantly maps from CXID to CXUID over and over each iteration, which is not very efficient. So in practice, you would hoist extension discovery out of a loop and do it once when loading the library or once per function call into the library. And as I mentioned, alternately, a CX-aware compiler can do these optimizations for you. An important dimension of composition is composition across the years. Sometimes the software client of an extension and the hardware implementation of the extension are separated by decades. Imagine in 2035 that a 2035 library is using an extension in CXU from 2023. or a 2023 library is using a 2035 CXU. In addition, over time, our understanding of the best composable extension API for any given problem domain will evolve. For example, there have been many flavors of Intel SSE and AVX, and at least 12 generations of Microsoft's 3D graphics APIs. So we must anticipate that a 2023 composable extension could change by 2028 and again in 2033. So how can we make that work well across the years with new and old libraries mixed in and using new and old extension versions? First, a library should only use the composable extension versions that it's been tested with. And a library may want to use a new extension if possible, but fall back to an older version otherwise. So in the spec, a composable extension is a named and immutable interface contract. If you make changes to an extension, for example, adding a new custom function instruction or changing the behavior of an instruction, you've actually defined a new composable extension. It was foo v3, now it's foo version 4. But all you have to do is give your new extension a new CX ID, which is just minting a new 128-bit GUID. Since a CXU may be able to implement old and new extension contracts for almost the same gates and LUTs, each CXU may implement more than one composable extension. This will be distinguished by a parameter CXU ID that's passed into the CXU core, a port on the CXU core. This also leads to a style of extension discovery in the extension libraries. A library will ask the runtime for the newest version of the extension that it knows about. If that's not configured, it might then fall back to ask the runtime for a previous version of the extension and so on. Thus, an extension library and the extension implementation, written by different organizations in different decades, can dynamically determine the best, most up-to-date extension that's mutually supported by both of them. All of this interface negotiation stuff seems pretty esoteric, but in my experience it works well. It's inspired by the Microsoft Component Object Model, also called COM. COM is Microsoft's framework for disciplined software component reuse, and it's used across hundreds of diverse libraries in the Microsoft ecosystem. It's been proven at scale for 3 decades across Windows and Office and DirectX games and so forth. So here are some COM ideas that are present in the composable extension spec. This notion of immutable interface contracts, self-named by GUIDs, components that can implement one or more interfaces, separately authored, separately versioned components that are substitutable and composed, and which enable multiple implementations of a given interface, and the use of dynamic discovery to find the best interface in a negotiation across time and space. Long industry experience with this model gives me confidence that this is a sound model for enduring composition of separately authored composable extensions. Now, having completed our exploration of the non-normative introduction section of the spec, we can now turn to section 2, the ZI-CX spec, enabling composable extensions at the hardware-software interface. The specification proposes 4 new CSRs for ZI-CX. We've already spoken about MCX selector and CX status. In addition, there are 2 more CSRs that support access control to extensions and their state. So let's start with MCX selector. This has 3 fields, a 1-bit enable, an 8-bit CXU ID, and an 8-bit state ID. The enable bit enables custom extension multiplexing. When 1, extension multiplexing is on, and custom instructions will issue CXU requests to the selected CXU. When 0, multiplexing is off, and the custom 0, 1, and 2 opcodes do whatever they already do on this particular CPU core. So this enables composing legacy custom extensions with newfangled composable extensions. The CXU ID field selects the current configured CXU. It's an index from 0 to the number of configured extensions minus 1. The state ID field selects the current state context within the selected CXU. Note that MCX selector is only accessible in machine mode. The CX status CSR accumulates error status flags carried back in a CXU response. It's read-write in all modes. Typically, software will zero this register, perform one or more custom instructions, and then read it back to determine if anything went wrong. Error flag fields in CX status are set when MCX selector is enabled and an error occurs during execution of a custom function instruction. If MCX selector contains an invalid CXU or state index, that will set CI or SI. If the selected state context is in the off state, that will set OF. Issuing a custom function that's not implemented in this CXU sets FI. An operation error, like a divide by zero, sets OP. And new private error state, such as per CXU error no, will set CU. If CU is set, a CX library will use iStateContext read status and read state to obtain the custom error state. The spec proposes two additional CSRs, MCX table and CX index, that allow privileged operating systems code to grant or deny unprivileged software access to composable extensions and their state. They also obscure other hearts extension usage, which denies certain side channel attacks. The purpose of these CSRs is to allow unprivileged software to change OS-managed CX selectors with one CSR write, with no OS detour. The privileged operating system creates for each heart a 4 kilobyte table of 1024 valid CX selectors. It maps the table inaccessible to unprivileged code and writes the table address to MCX table CSR. The privileged OS then manages table entries and returns opaque table indices to unprivileged code. The unpriv code cannot write MCX selector, but can write CX index. In response to writing CS index, the CPU loads the corresponding MCX table entry using the next privileged mode access and writes that selector value into MCX selector on behalf of the unpriv code. Still to be determined is whether all ZICX systems must implement all 4 CSRs, or whether austere M-mode only processors can leave out these 2 access control CSRs. And also still being discussed is which CSR write instruction to use to change selectors, a write to MCX selector or a write to CX index. Now, we've already introduced these 3 custom function instruction encodings that are used with extension multiplexing. Note there's considerable interest in redesigning these particular opcode assignments, which bits will go where, and so on. There's interest in making the register field dependencies optional, in signaling that a given instruction is stateless, or safe to issue speculatively, and so forth. Please refer to some notes in the spec. Also, looking ahead, we may decide to dedicate some custom opcode space for non-multiplexed access to conventional custom extensions and some other parts for these composable extensions v1, as well as to keep some in reserve for future composable extensions versions. We must be careful and precise about interactions between instruction execution in the CPU pipeline and of custom instructions. The spec promises an implicit fence between CX CSR accesses and any subsequent custom instructions, and vice versa. So for example, a CSR read of CX status must await CXU responses from any prior custom instructions. Similarly, there's an interaction between precise instruction exceptions and speculative issue of stateful custom instructions. Please see the notes in the spec. The specification proposes a standard interface iStateContext with 4 standard custom function instructions that read and write extension status and state. Each stateful composable extension must implement these 4 custom function instructions. Read status and write status access a standard state context status word, indicating the operating status of the extension. The CS field can be off, initial, clean, or dirty. This echoes mstatus.xs. The state size field indicates the state size in xlen bit words necessary to perform a context save of this stateful context. And the .error field is an 8-bit error no for the extension's most recent stateful error. The read state and write state custom function instructions enable an operating system to uniformly save and restore a state context of any stateful custom extension. The next section of the specification defines the standard hardware-hardware interop interface, called the Composable Extension Unit Logic Interface. First, let's review some CXU-LI design objectives. We want an ecosystem of composable extensions, and that requires modular, reusable, platform-neutral extension hardware cores, our CXUs. We must be able to automate composition of complexes of CPUs and CXUs, and do so without having to change or revalidate any CPU or CXU RTL. We must handle diverse CPU microarchitectures, from simple MCUs up to complex, out-of-order multi-issue processors. And diverse extensions, with ALU-like functions, or even with deeply pipelined stateful matrix multiply-like functions. The interface signaling must be extremely gate and LUT frugal, so they're affordable in tiny systems and affordable in many core systems. And as before, we must promote uniformity, uniform port signals, naming, parameters, reusable validation tests, and uniform CXU metadata. Here are CXUs in a nutshell. A CXU implements one or more composable extensions. A CPU issues some custom function instructions. Each becomes a CXU request that's routed to the selected CXU, which performs the requests in order, possibly updating state, and sends CXU requests back to the CPU, which updates destination registers and the CX status CSR. CXUs are highly configurable, with parameters like port widths, latency, and state context counts. And the valid parameter values for a CXU are described in its CXU metadata. The CXU logic interface supports different CXU feature levels, reflecting different levels of sophistication of CXUs. It efficiently supports combinational CXUs, pipelined fixed-latency CXUs, variable-latency valid-ready handshake streaming CXUs, and response reordering CXUs. A given CXU or CPU will all speak a specific CXU-LI level. And then systems are composed from these using parameterized switch and adapter CXUs. The 4 CXU feature levels are stratified to factor out boilerplate complexity and overhead, to keep simple cases simple and frugal, while still supporting complex use cases. Therefore, we care about and support well and efficiently simple and complex CPUs and simple and complex CXUs. Level 0 is for combinational CXUs, with ports signaling the requested CXU, function, and data operands, and with response data and status. Level 1 is fixed latency clocked CXUs, which add clock, reset, clock enable, a state ID, and a response valid. Level 2 is for variable latency streaming CXUs, adding valid ready handshakes on requests and responses. And level 3 is for response reordering CXUs. The CXU-LI enables automatic composition of CPU and CXU complexes. Composition configures the CPU and CXU RTL modules with compatible parameter values, and then inserts switch and adapter CXUs to wire everything together. This is powered by CPU and CXU package metadata, which defines feature levels and feasible parameters for each component. Since both CPUs and CXUs can issue CXU requests upon other CXUs, the CXUs in a system will form a directed acyclic graph. In this example, there are 2 CPU cores. Each can issue requests to any of 5 CXUs. Each CXU implements one or more composable extensions. In this figure, notice the angle brackets notation, which indicates how many hearts or state contexts are configured in each component. Here, each CPU core has 2 hearts, for a total of 4 hearts in the system. Therefore, the system designer has built the system manifest specifying that each stateful CXU will have a separate state context for each heart. So CXU0 and CXU2 each have 4 state contexts. CXU1 has 8 state contexts, 4 for the CPU hearts and 4 for the 4 state contexts of its CXU2 client. CXU3 and CXU4 are stateless and will have 0 state contexts. Note that CXU3 is at feature level 1, while the rest of the components are feature level 2. Therefore, the first step of composition is to insert an adapter core to raise CXU3 from level 1 to level 2. Now all that remains is to insert switch CXUs. The first routes requests from the CPUs to all of the CXUs, while the second routes requests from the CPUs or CXU2 into CXU1. In summary, composition of CXUs is a configuration constraint satisfaction problem. And in some cases, there is no feasible solution. For example, if a CPU can only support a CXU latency of 1 cycle, and a CXU can only support a CX latency of 3 or 4 cycles, automatic composition will fail. Here we recall the custom extension multiplexing figure presented earlier. Let's consider how that translates into the port signals of CXU-LI. Reviewing the request and response ports in the table on the right, request ID is provided by the CPU itself. Request CXU and state come from the MCX selector. Request instruction and request function from the instruction. Data 0 and data 1 from the register file or an immediate. Then the response ID is just the request ID that was received. Response status will then be merged back into the CPU's CX status, and response data written back to the destination register. This table summarizes CXU-LI request and response port signals. For each port, we see at what feature level that port is introduced. Some ports have a configurable width parameter. For example, you can configure the CXU data width to be 32 or 64 bits wide. Some ports, such as the raw instruction request port, are optional and may be deleted with a width parameter of 0 bits. Now we'll briefly consider the 4 CFU-LI feature levels with some simple waveform examples. The first is CXU level 0 combinational CXUs. This supports only stateless extensions because there's no clocking. It computes a combinational function of the request function and the data, and it sends a response status and data after some delay. CXU level 1 supports fixed latency clocked pipelined CXUs. The CXU computes a function of each request and its private state, if any, possibly updating the state, and sends a response after the parameter CXU latency cycles. Some CXUs can support a CX latency down to 0 cycles, meaning they can respond in the same cycle as the request. The initiation interval is 1 per cycle, so the CXU can process a request every cycle, and there's no flow control. Clocked CXUs do have an optional clock gating to save power. Negating the clock enable input suspends the CXU interface and internals. This works well on FPGAs whose flip-flops all have a free clock enable input. In the waveform at right, the CXU has a CXU latency of 2 cycles. The first 2 requests arrive in cycles 1 and 2, with responses in cycles 3 and 4. The next 2 requests arrive in cycles 5 and 6, but then the clock enable is negated, and so the final 2 responses are received in cycles 21 and 22. CXU level 2 is for variable latency, or streaming CXUs, which compute a function of each request and its state, if any, possibly updating the state, and then sending a response in order in a later cycle. Both the request and response have valid-ready handshaking flow control, so the CXU can suspend incoming requests, and the CPU can suspend incoming responses. Of course, this significantly impacts the design of a CPU or a CXU, since each must tolerate this flow control suspension of the request or response channels. This kind of CXU is apt, for example, for a pipeline floating point unit, which might have a pipeline multiplier with a latency of 3 cycles, a pipeline adder with a latency of 5 cycles, and an iterative early out divider unit with a variable latency. The waveform at right shows 4 incoming requests and 4 outgoing responses, and the effects of handshaking and response latency on those requests and responses. CXU level 3 is for streaming CXUs that may reorder responses. It still computes a function of the request and state sending a response, but responses may occur out of request order. This only occurs if the requests are to different state contexts or in a stateless CXU, whereas in a stateful CXU, a series of requests to the same state context are still always sent in request order. To correlate responses to their requests, CXU level 3 adds request and response ID ports. The CXU will return the incoming request ID as its response ID. Now, the stateless pipeline floating point CXU of the last slide would also be a fine response reordering CXU. For example, receiving 3 requests to divide, then add, then multiply, it might respond out of order with the product, the sum, and then the quotient. This reordering can greatly improve CPU performance, assuming of course the CPU is also at CXU level 3 and can tolerate out-of-order responses. CXU-LI-compliant CPUs implement ZICX composable extension multiplexing, issuing custom instructions as CXU requests and accepting CXU responses. The CPU's CXU-LI level caps which CXUs it may be composed with. For example, an austere single-cycle CPU implementing level 0 can only be composed with combinational CXUs, whereas pipelined in-order CPUs might implement level 1 with some fixed CXU latency that its CXUs must match. Or it might implement level 2 with valid-ready flow control, suspending its pipeline when a CXU negates request ready, and itself negating response ready if there's a cycle in which its register file writeback is busy and a response cannot be accepted. And a complex out-of-order completion CPU might implement level 2 or level 3, enabling those more sophisticated CXUs. To enable automatic composition, CXU-LI provides pre-built feature-level adapters. Each translates higher feature-level requests and responses and forwards them to the lower-level CXU. As with all CXUs, they're configured with various parameters. The 3 adapters are convert01, which raises a combinational level 0 CXU to a pipelined level 1 by adding a configurable CXU latency response shift register. Convert02 raises a combinational level 0 CXU to a streaming level 2 by adding a response register plus valid-ready handshake logic that can suspend incoming requests when it has response data pending but outgoing responses are suspended. And Convert12, which raises a pipelined level 1 CXU into a streaming level 2 by adding a pending responses queue that buffers pending responses back from the pipeline CXU when outgoing responses are suspended. For more details, including their RTL implementations, please refer to the spec and the GitHub repos zoo subdirectory. Automatic CXU composition also employs CXU Switch cores that are configured to compose one or more initiators with one or more targets at some fixed CXU feature level. Switches use sets of arbiters and multiplexers to transfer eligible request inputs to available request outputs, routing requests to their downstream CXUs, and similarly routing incoming downstream CXU responses back up to the respective initiators. This example has two CPU initiators with a 2x2 switch targeting two CXUs. The code below left is running on each of the two CPUs. Each writes its heart's MCX selector for CXU ID 0 and issues two custom instructions. Then writes MCX selector for CXU ID 1 and issues two more custom instructions, and loads MCX selector with CXU ID 0 again and issues a fifth custom instruction. The busy waveform at the right illustrates the request and response streams and the handshakes seen by the two CPUs and the two CXUs. Please refer to the spec for more detail on this. CXU Level 2 and Level 3 request and response channels, each with valid-ready handshaking, can map nicely onto two AXI4 streams. This is very useful because modern SoC infrastructure provides many AXI4 system interconnects to transport AXI4 streams about the chip. For example, in the AMD Versal devices, its NOC speaks AXI4 streams. Therefore, the specification defines a canonical port mapping between CXU-LI request and response streams and AXI4 request and response streams. This will allow simple and frugal configurable standard adapters to bridge the CXU-LI world and the AXI4 streams world. So this concludes the exploration of ZICX and the CXU-LI sections of the spec. From section 4 onward, the rest of the spec is more preliminary and incomplete. The design employs metadata to power automatic system composition. Each CPU and CXU RTL module is accompanied with a metadata description of that component's properties, features, and feasible values for its CXU-LI parameters. Then the composer can input all of the package metadata and the system manifest and solve to find a feasible assignment of all parameters. Then emit the composed system RTL and the system CXU map. The spec currently uses YAML for a CXU metadata schema and to describe CXU parameters, constraints, and properties, such as feature levels and numbers of state contexts. Even though the composable extension runtime library is an essential part of the composable extension hardware-software stack, it's yet to be fully specified nor implemented. However, we can describe the minimal set of services that the CX runtime must implement. This simple CX runtime interface sketch defines four data types: the CX ID, which is a 128-bit globally unique ID, and the CXU ID, state ID, and CX selector, which are all 32-bit integers scoped to a particular system configuration. The runtime must provide at least a discovery API to map a CX ID into the CXU ID on this system. state context management functions to allocate and free state IDs per heart, selector management to make selectors from the CXU IDs and state IDs, and a function to change the heart's current composable extension selector. This latter function might be an inline assembly function and compile to a CSR write of CX index, or perhaps in machine mode code, MCX selector. So where are we at and what's left to do? As of August 2023, we have a solid draft spec for ZICX and CXU-LI, but much more work to do to demonstrating the specification working in hardware and software. The project repo now includes a CXU zoo with RTL implementations of some CXUs and CXU adapters. For example, we have a combinational population count CXU and a pipelined subword parallel dot product CXU, as well as the 3 level converters 01, 02, and 12, and a level 2 switch. I think our compelling end goal will be a multi-CPU, multi-CXU, multi-library, multi-platform plug fest, but we still have much to do to design, implement, and test to get there. We've restarted discussion in RISC-V International's SIG-Soft CPU group. A renewed consensus there will take time. We hope to launch 2 new task groups within RV International, an ISA task group for a ZI-CX spec and a non-ISA task group for CXU-LI. We have to overhaul the metadata work and build a CX runtime and a simple composition tool. We're going to have to discuss forward-looking V2 work so we don't paint ourselves into a corner with V1. And we need to add ZICX and CXU-LI ports to a few of the open source RISC-V soft processors. We need some more CX libraries to target our zoo CXUs. And we need to add more CXU examples to the zoo. Perhaps we'll adapt some of the CFU playground CFUs. Much of this is prerequisite for that first demo of correct automatic composition of 1 CPU, 2 CXUs, and their CX libraries. Then several more CPUs, custom extensions, CXUs, and CX libraries will be needed to enable this mix and match plug fest. Once we have that first plug fest, though, the composable extension ecosystem should be well underway, and eventually its network effects will lead most CPU, custom extension, and library developers to adopt these common standards. Finally, one last slide. If you think the RISC-V ecosystem would be stronger if multiple agile composable custom extensions could coexist correctly within one system, if you think it should be painless to add another composable extension into your system, if you want every new RISC-V CPU core to have immediate access to a rich catalog of composable extension packages and extension libraries, if you want applications that use composable extensions to just work and to keep working over the years, and to be easy to integrate new versions of extensions, if you're concerned that RISC-V may be adding too many standard extensions to the enduring complexity of the platform, if you think we all ought to be able to share and build on each other's good work, if you think we need fewer silos and less fragmentation of our ecosystem, then I hope you'll participate in, or at least support, our proposal to start 2 new RISC-V International task groups, the CX ISA task group and the CXU-LI task group. For our part, we'll submit our draft composable extension specification. So, what do you think? Do you have questions, suggestions, or criticism? Please let us know either via our GitHub repo or by participating for now in the RISC-V International SIG-Soft CPU group. I hope to see you there. Thank you very much for your interest, and have a great day.